Hi, we are from Group B7, and in this video we're going to explain about Experiment 2, Solid Phase of a 3-component system. In this experiment, the objectives are to be able to understand that a 3-component system can be represented by a triangular phase diagram if temperature and pressure are constant. Secondly, in this experiment, we are to be able to know the method of plotting, labeling, and using the 3-component phase diagram. For introduction and theory, a Gibbs phase triangle can be used to depict the phase behavior of a ternary system on a 2-dimensional diagram, where it is important to consider both temperature and pressure are fixed. We can independently change the pressure, temperature, and 2 independent composition variables for the system as a whole. The phase of the system as a function of composition can then be shown. The relative amount of 3 components, normally in weight percentage, can be shown on the triangular plot as shown in figure 2.1. So here is the figure. 3-component phase diagram has the shape of a triangular prism with an equilateral triangle as foundation, which is known as a composition triangle. In figure 2.1, each apex of the triangle indicates one of the pure components A, B, or C. Point on the side of the triangle opposite the vertex represents a binary system, while the point within the triangle represents the ternary system. The side of the triangle opposite the corner, labeled A, for example, shows there is no A. Hence, the horizontal line across the triangle shows an increasing percentage of A from 0 at the base to 100% at the apex. Similar concept is applied to percentages of component B and C. Ternary system involving solid and liquid can be explained by considering the system of 2 salts and water. The 2 salts, for example, NH4Cl and NH42SO4, are partially soluble, and the diagram gives a binodal curves for the saturated solution composition in figure 2.2. In this figure, tine line AB and CB show that saturated solution and the 2 solid salts are in equilibrium. Point B represents a system where both solid salts are in equilibrium with the saturated solution. The removal of water at point B will result in lowering of total composition towards the base of the triangle, where more solid salts will form in order to maintain equilibrium with the loss of water.
So, let's go through the procedures of this experiment. First step, the following solutions were prepared in a separate closeted test tube. Next, NaCl salt was added into solution 1 and 6 until a saturated solution was formed and a layer of insoluble crystal was settled at the bottom of the test tube. Meanwhile, NaNO2 salt was added into solution 4 until a saturated solution was formed and an insoluble layer of crystal appeared at the bottom. The third step, the lid was attached and the test tube was shaken one by one for a minute, alternatively for at least 15 minutes. The solution was filtered with a filter paper into a 50 ml conical flask. Next, a glass stopper was placed on top of the conical flask and heated slowly on a hot plate to evaporate the water. Next, the sample was then dried in an oven. And the final step, the dried crystal was allowed to cool at room temperature and the yield was weighed. The drying process was repeated until the yield reached a constant mass.
Moving on, we're going to explain about the results. So from the experiment, we get a table data of mass of conical flask with sample before and after heating, and the mass of product crystals for solution 1 to 6. And from the table, we can do calculations. Here are the calculations for solution 1, solution 2, solution 3, solution 4, solution 5, and solution 6. Finally, by tabulating all the data from previous calculations, we get a table of saturated solution composition in weight percentage for solution 1 to 6. And from table 2.2, we can construct a ternary phase diagram as shown in figure 2.4 at the right. From the phase diagram, invariant point is plotted where it consists of 47.5 weight percent of H2O, 39.8 weight percent natrium chloride, and 12.7 weight percent of NaNO2.
Based on the graph, the compositions and phase behavior of NaCl, NaNO2, and H2O are represented. The binary phase system was established once the cloudiness was observed, showing that the solution was saturated with known salt. All points in the diagram represent saturated solutions. The lines in the diagram represent compositions at which two salts are in equilibrium with the same liquid phase. This is known as the invariant point. The invariant point in the graph is plotted at 47.5% H2O, 29.8% NaCl, and 12.7% NaNO2. Here, both salts, NaCl and NaNO2, coexist at equilibrium with water at fixed pressure and temperature. The phase diagram of a three-component system consisting of NaCl, NaNO2, and H2O can be constructed when there is minimal experimental error. From the ternary phase diagram, the invariant point was plotted at 47.5% H2O, 39.8% NaCl, and 12.7% NaNO2 at room temperature. The phase rule was used to relate the usage of triangular coordination in the ternary phase diagram to determine the mutual solubility of liquid in a two-component system.